Okay, welcome to the last week of numerical algebraic geometry. This week we cover a very coarse description of certification methods that exist. I'm not going to get into the details about them, but I'm going to give you enough information so that you can intelligently interpret the output of the existing software for certification, and you know what to be careful about as a user. Okay. So first things first. What could we possibly want from a certification method? Okay. So let me try to drop the scope down. We have a univariate polynomial of degree 10. I have a numerical approximation, x, of a root of this polynomial. Okay. What could I possibly hope for in terms of a rigorous mathematical statement? Like, what do you even want? Close enough for what?
Give an approximate value.
Some measurement maybe of how close the approximate solution is. That'd be good. So maybe I don't know what close enough means. Maybe what's close enough for my application isn't close enough for my neighbors. But maybe I can say, hey, there is a true root, which is at most this far away. That would be a rigorous mathematical statement, right? What we really want, of course, is that x something like this. But this is our usual polynomial system. We're not going to get it, of course, because we're not going to be able to represent algebraic numbers of pi degrees with floating points. Exactly, right? So what are we going to settle for instead? So here's one thing we'll settle for. We know that as long as we're close enough, whatever this means, to a true root of a polynomial system, Newton's method applied to our approximation will converge quadratically to some true root. What does converge quadratically mean? Yeah. So it means I apply Newton's method k times, and I'm within 1/2 to the 2 to the k minus 1 times how close I was to start with. Okay, so that's what it means for a Newton sequence to converge quadratically. So this was from our first chapter. And when that happens, we'll say x is an approximate solution with associated true solution, squiggle C, whatever you want to call this. Okay. There. So in other words, if you have a solution to a polynomial system, there exists some funny shape around it, such that anything inside that funny shape will converge quadratic. Okay, so that's what close enough means. If you'd like, there exists some ball, such that anything in that ball will converge quadratic. And if you ever get a chance, go ahead and do a Google image search of Newton's method. You'll get all these gorgeous pictures where you have some univariate polynomial, you have like n roots, and you color the complex plane by n different colors depending on which root that as the starting point converges to under Newton's method. And you will indeed see these regions surrounding the roots, which are really nice. Okay. And these are called the basins of quadratic convergence. Maybe we'll take a look at one later. So the other thing we'll settle for is a box. I.e. something that looks like an interval over the reals. And an interval over the complex part. Okay, so in reality, our numerical approximations are so close that I wouldn't be able to draw a distinct point on the board, of course, so I'm gonna be exaggerant in our numerical failure, so that X is our numerical approximation of the true root. Okay, so that X is also denoted X. This is C, and Newton's method applied converged superfast C is the first statement. The second statement is that I'm gonna find a box containing X, and I'm gonna prove it contains a unique root of F. So those are the two kinds of statements you're gonna get out of state-of-the-art certification methods. And this is all only gonna work, at least out of the box, for square polynomials and equations and variables. Yeah, go ahead.
Can you tell me, I understand what the words means, what are the other two neighborhoods in the picture?
So this big neighborhood out here is basin of quadratic convergence. So you can look at all the complex numbers for which this holds.
Mhm.
Color them all, you'll get some funny subset of the complex, which we know contains an open ball surrounding our solution, provided that our solution is a regular solution.
Right.
The box then is some interval, which will it'll serve the purpose of our certificate for our numerical solution. The ball here indicates that the basin of quadratic convergence is open. Like there is a neighborhood of your solution which lives in the basin of quadratic convergence, and then the dots indicate some Newton sequence converging super fast. That's any other? Great. Yeah, so this is what we're hoping for now. So we wanted a statement that says our numerical approximation is actually a root of our polynomial system. That's of course impossible as soon as you realize that not every number is rational, and so you settle for this. Okay. So as far as implementations go, at least, number one came first, and is based on the alpha theory of Smale. The first software implementing it, as far as I know, is Alpha Certified by John Hongstein and Frank Satile. And then the second method, the underlying math for that is a so-called Krawczyk's method. I know I should pronounce that better with a Polish last name myself. But yeah, just cross check. And this is based on so-called interval arithmetic. So this second one is coded in homotopic continuation in Julia, and it's exceptionally fast. So it's about as fast to produce these certificates if they exist as it is to actually solve the system, in my experience. On the other hand, the Alpha certified software was state of the art in the sense that it was the first software where you could actually certify numerical results and use numerical algebraic geometry and prove things in algebraic geometry using. So let's go over alpha theory first. So the setup is we have a square system. This is what Newton's method looks like. And we define these three constants, alpha, beta, and gamma. That's where you get alpha theory from. Okay. So what's alpha? Okay, it's the beta times the gamma. Well, what's the beta of some solution with approximate solution with respect to our system? It's just how much we move under Newton's method. What's the gamma? Something else. You can compute it, ignore it. Sorry, rather than computing it, you can bound it by something you can't compute. Okay, and I don't want to go into the details here. Okay, but there are these three constants. The first one's the product, the second two, these can both be bounded. Okay. And the statement is as follows. We have a polynomial system. You have some points. You hope there's an approximate solution in the sense that it converges quadratically to a true solution. The following is true. That's it. That's the big alpha theorem. You have a square polynomial system. You have some candidate solution for which when you evaluate alpha, you're smaller than 13 minus 3 square root of 7 over 4. Mysterious number, I suppose. Check out the paper. It's about 0.1576. Kind of nice that it's this universal constant. All right. But as long as you're smaller than that, then X will be an approximate solution to F. Moreover, the true solution is at most 2 beta O. Okay, so that's so this satisfies hope 1, this satisfies Michel's hope. Okay, that we can actually quantify the distance between the true solution, that we can articulate how close to. And from that, we can then judge whether or not we're close enough for whatever application we're interested in. So, draw this picture again. Some true solution out there. Okay. Approximate solution X. Okay. And you can look at the region of the complex plane where this alpha value is sufficiently small. And the X converges to this through root C. And it's really, really small compared to the basin of quadratic integrals. So that's the thing you should know. As far as like qualitative features of this procedure, this is a pessimistic bound. very often this alpha inequality is not satisfied, and nonetheless, you still converge quadratically. So just because alpha isn't bounded by this number, doesn't mean it's not an approximate root. But if it is bounded by this number, then it is an approximate. Okay? So I compute the alpha, and I either get yay, hip hip hooray, I'm smaller than 0.15767, in which case I know that my true root is within 2 beta x. Oh.
And that's the beta.
That's the big. Notice that it shrinks very fast also, as I apply Newton's method to x. So, for example, if I wanted to tighten how close I am to the true root, I would just apply Newton's method. Okay, and then my alpha is going to shrink, my beta is going to shrink quadratically half, right? And so I can really get arbitrarily tight bounds on where the true root is, just by applying Newton's method and then running the evaluation of alpha, beta, gamma again. Okay, so let's get a running example in our head. We have some polynomial system that's square, and we want to do some like certification. So let's take the 27 lines on the cube. 4 equations, 4 variables, 27 solutions. Okay. The first thing you'll notice, as far as the distinction between the problem of 27 lines on a cubic and my picture, is my picture is in C. Solutions to the problem of 27 lines live in C to the 4. All of this applies for more than one variable. Push it, like as written, it's in more than one variable. Okay. Balls in the complex plane become balls in C to the n. Everything else, yeah, distance in C becomes distance in C to the n. This mysterious thing can still be computed. This is still the definition of quadratic convergence. Okay. So I take my 27 numerical approximations. For each, I compute the alpha, beta, and gamma. And I conclude that all 27 are indeed approximate solutions to the system. Okay. That's great news. What mathematical statement can I then conclude? Can I conclude that I found 27 solutions? Well, okay, so 27 numerical solutions, 2. Again,
None of them are identical. Everyone distinct. What do you think?
maybe. I don't know. We haven't said anything about whether or not they're distinct. So yeah, Deepak hit the nail on the head there. All I know of this is that each converges quadratically to some true. I have no idea if they're distinct. All right, so I cannot, for example, confirm or deny whether or not there are at least 27 solutions to this system yet. I need some method for verifying distinctness. Right? Well, there is one staring at us. Right? So I can get arbitrarily close to my true solution. This beta can get smaller and smaller and smaller. So back. I guess for that. If x1 and x2 are approximate solutions, And the distance between x1 and x2 is larger than what? Beta. X1 is beta at x2. Then their associated roots. Roots are distinct. Why? Okay, so I got some x1. That's 2 beta 1, right? I'll just call beta 1 beta fx1. I have some x2. 2. If this distance is larger than both of these distances, then these circles can't touch. And I know x1's associated root is in this ball, and x2's associated root is in this ball. They have to be distinct. You get a separation bound. So star is being able to is the corollary which allows you to separate your roots. So you can confirm pairwise that they're all distinct using star. And if it doesn't work because you have some solution where they do intersect, right? So if this inequality doesn't hold, well, that's fine. Just hit it with Newton's method a bunch. You'll be fine. These balls are going to shrink super duper fast. Then you can conclude that F has at least 27 negatives. You actually place them in those little itty bitty balls in your solution space. So we can get lower bounds on the number of regular solutions to polynomial systems this way. Almost. See some furrowed brows. My brow would indeed be furrowed. That was sitting where you are. There should be one big concern. Let's take this beta before. So beta is the distance between my numerical approximation and where I am after applying Newton's step laws. I said I could evaluate that. Of course I can evaluate. I have x, I can apply Newton's method, I can take the distance. Okay. At what point should I be concerned about my evaluation of beta if I'm giving floating point solutions? Right, so I'm going to lose accuracy when I evaluate Newton's method. Not in the sense that my evaluation of Newton's method is going to be less accurate than what I had before. It's going to be more accurate. However, part of Newton's method is evaluating a Jacobian, which has floating point entries, taking the inverse, evaluating the system. So that's not going to actually be philosophically sound here, right? There's still just an itty bitty hole in the bottom of this epistemological pail, okay? And the water falls out, okay? You can try to evaluate these things and you'll get good floating point approximations, that's fine. Doing that and obtaining these bounds is a so-called soft certificate, and it gives you an idea of whether or not your numerical approximations should even be attempted to be certified. But at the end of the day, you are still going to need a rational candidate solution and a rational polynomial system. Almost all polynomial systems which come your way are going to be over rations, even if you're working in applications. If you're working in applications, you get some floating points. Turn those floating point numbers into parameters and think about it as a rational polynomial system evaluated at floating point parameters. Okay, so really almost all of your polynomial systems you write down are going to have rational coefficients. So this part isn't too scary. And it's not too scary to get a rational approximation for my roots either. I already have numerical approximations, right? Some x2. But there's this wonderful fact that the rationals are dense in the roots, right? And so rationals plus imaginaries times rationals are dense in the complex plane. In other words, I can arbitrarily approximate this, my numerical solution, by something that looks like a rational number plus I times a rational number. Okay? And there's various methods to do this. The most naive way is to just slice off that floating point approximation, multiply it by a big power of 10, and then divide by a big power of 10. You know, there's a rational number. There's smarter ways to do it using, oh my gosh, continued fractions. Continued fractions is a very, very smart way to get rational approximations of floating points. So that part's not too bad. The problem is that as soon as you approximate your numerical solution by rationals, you may have rationals with very large integers in the numerator and very large integers in the denominator. And performing all of these evaluations actually now becomes prohibitively expensive. Okay. But what you win for the cost of your time and energy and computational power is that you get a proof. Okay. So you use arbitrary precision integers to represent rational numbers. So you don't have to worry about overflow, it just takes a long time to add them. And you evaluate these things, obtaining a proof of this fact, and therefore obtaining a proof of the conclusions you draw from that fact. And this is what is implemented in the software Alpha Certified. And yeah, it takes a while for it to run this computation and draw its conclusions. However, you do get proofs. Okay, the other thing to note that is that if your input polynomial system is real, in particular if it's rational, that's real, then Newton's method is a real operator. And so you can actually do the same business over the real numbers and be able to conclude which solutions are real. Okay. There's another trick to talk about real solutions, which we'll talk about now in the context of interval arithmetic, because yeah, we have time. Right, so this also will tell you the number of real solutions. So lower bound on number of real solutions. Maybe I want to say let me think, so one more thing here is that, it is very hard to obtain a proof of the number of solutions to a polynomial system. A priori. In general, if you really want this, you're gonna have to like either do some theoretical mathematics, or if you want to brute force it, you compute a Grosvenor basis. But Grosvenor bases take a long time. Okay. Now you can do it numerically by just trying to find all the solutions, and you do it a few times maybe, and then you can bet your life savings that you're correct, but it's not a proof. But the other thing to remember from our parameter continuation story is that it's very cheap to get an upper bound on the number of regular solutions to a polynomial system. Very cheap. You can look at a polynomial system and say, yep, that's got at most this many regular solutions. It's the Bézier bound. And if you want it to get tighter, there are tighter bounds, right? You can do the mixed volume and use the BKK theorem. You can say, yeah, there is at most this many isolated solutions in the torus. Certification affords you the ability to get a lower bound. And so for many, many, many systems, these coincide. So you're either Bézier sharp in the sense that you really do have Bézier many solutions, or you're BKK sharp in the sense you really do have BKK many solutions, right? Or maybe you just theoretically know the degree, right? As soon as any of those are the case, and you do number one, and it coincides with either your upper bound that you've computed or the known degree, you don't just conclude that you've counted the number of regular solutions, you conclude that you have found all of them. You know there's at most this many from theory, and from your certification, you know there's at least this many distinct ones. Okay, and so you conclude there's exactly that many, and I have found them, and I've isolated them in C to B via my beta balls here. All right. I'll move on from alpha theory and move on to interval arithmetic, which is the basis of the computation done for Krofft's method, which is implemented in homotopy continuation. And it's what's going on behind the scenes when you call the function certified. Okay. Interval arithmetic. Pi, never going to represent that by a floating point number. So that's a problem. E, no chance there either, not even algebraic, famously. But here is something everybody knows. It's somewhere between 3 and 4. Okay, and here is something that everybody knows. This is something between 2 and 3. Great, and so now we have this amazing thing we can do where we can say that 2 pi plus 3e has to live in some interval as well. Anybody got it? I'll leave this up.
Oh, 2
Plus 12 plus 9. Somewhere in there, great, cool. The elementary school teachers call this number sets. Okay, I have a sense of generally what this is. It's not going to be negative, right? Okay, this is called interval arithmetic. And of course, our exercise just proved that it's much easier to just implement this on a computer, and it should be no problem. Indeed, so we can add intervals together. You all did it naturally. You take the smallest number in the first summand and add it to the smallest number in the second summand, largest to the largest, etc. And you can ask, okay, well, how can I do this with multiplication? It's a little bit more complicated, or division, it's a little bit more complicated, or complex operations, a little bit more complicated. But the point is that there exists a way where if I have some box, right? So there's A and B. There's C and D. representing a little area of the complex plane, I can do multiplication, division, addition, and subtraction with other intervals, and guarantee that the result lives in some desired interval, okay? So I can evaluate it, this interval, for example, at a polynomial. And that might conclude that if x lives in this interval, then f of x has to live in that interval. We'll call this I. This is called interval arithmetic. So, fundamental tool in numerical analysis. Because what are you doing? You're really controlling error here. You're like, yeah, if I'm like within this error tolerance and the reals and the imaginary, and when I apply a polynomial to this number, now I'm within these tolerances. Any questions? Anybody take algebraic topology? Yeah. Yeah, you thought?
No, not this time.
Anybody know what Brouwer's fixed point theorem is? Anybody hear it?
Function in the disk to itself
Good,
as a fixed point.
Yeah.
awesome.
That's,
That's to be what?
no, I saw it from a the time.
This is Brouwer's fixed point theorem. If you have a continuous map from a disk to itself, okay, think closed ball. Let's see to the end, to itself. It's got to have a fixed point. Okay, so it's got to have some input where after you apply that function, it hasn't moved at all. And then the standard thing to do pedagogically here is to take up a piece of paper, right? Acknowledge that this piece of paper, every point on it has some coordinates on the table. And now this is a continuous mapping. And so there's some point on this piece of paper, at least one, which has the same XY coordinate on the table, even after the crumple. Maybe two, maybe infinitely many. But since crumpling up a piece of paper is a continuous map, that's the thing I'm supposed to do. Okay. Bonne's just fixed point theorem is one you probably have here. It says that a contraction of a disk to itself has a unique fixed point. A contraction mapping is one that shrinks distances at some universal constant. Okay, so x and y are in my disk, they're d away, then d of x and d of y are going to be k times d away, where k is less than 1. Okay? And it doesn't depend on x and y. I can pick any x and y that's the same k. That's what a contraction is. Okay. In particular, this disk is getting mapped into itself. Right? So you imagine if you do it over and over again, so you're shrinking, 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 hence the name contraction. Perhaps it's no surprise that the diameter of this thing is getting smaller and smaller and smaller. You're in a metric space, you're going to converge to a unique thing. Right? And then that will be your fixed point. That's Bonne's fixed point. Subtly different than Brouwer's. Okay. We are almost there. We almost see the whole story now. That's the map we consider. Newton's method is a continuous map which will gobble up complex numbers and spit out complex numbers. And I can restrict Newton's method to I. Right? So here's my approximate solution. Now I throw an interval around it. not one with like pi as endpoints, one with rational endpoints. I can actually do exact computations. Okay. And I apply Newton's method to it, to my polynomial system. Not on my approximate solution. I mean, I've been doing that all day since the beginning of this course, but on my interval. Okay. So here's I just copied it over. And it could be that what pops out is an F. Okay. And if that's a contraction, then I would know it has a unique fixed point. And what are the fixed points in Newton's method? How about in the univariate case? X goes to X, but we got to change it by f of x over f prime of x. So I'm changing it by nothing. I'm a root. The fixed points of Newton's method are roots. Roots can be thought of as fixed points. So that's the idea. So if I prove that Newton's method is a contraction mapping on my itty-bitty interval that I've chosen, surrounding my approximate solution, then I've proven via Bonnach's fixed point theorem, thank you pure math, algebraic topology, that there's a unique root in that box. Cool. So it turns out this never works. But there's a small adjustment where you replace a Newton's operator with the cross-check operator, and you're good to go. Okay, so morally, this is what you think of. In reality, it's not really what's, I mean, it's kind of what's going on, but you can't just directly do interval arithmetic here. You won't ever get a contraction, so you need to use a cross-check operator. And this is all implemented in homotopy continuation. You can plug in an approximate solution to your polynomial system. It will find a rational bounding box for every coordinate. It will evaluate this cross-check method, cross-check operator, and it will ascertain whether or not the interval it gets is contained in the interval it started with. If that is the case, it will say your approximate solution is really honest to goodness an approximate solution of a unique solution in this box. So again, we're getting bounding boxes. Where we got bounding balls, and we got bounding boxes. This is super duper fast. And again, we can obtain lower bounds on the number of regular solutions. We can obtain lower bounds on the number of real solutions. Oh yeah, how do we get real solutions? Well, if I have a real root and I have a numerical approximation of it, in particular, my numerical approximation will not be exactly on the real axis. I'll have some really small number times complex. Right? Okay, so let's take a bounding box. It'll probably contain a portion of the real axis, right? And now, so that's I, that's X. Now let's look at I bar. Okay. So if X is not real, then I bar is going to contain a solution too, provided that my system is over the reals, because non-real solutions come in conjugate pairs. Okay, so I already know symmetry. I only have to do half this work. Okay. And in fact, I can always shrink my intervals and have a better chance at being a contraction map. So let's even make it so that they don't intersect each other, for example, right? So if they intersect along this axis, and I prove that there's a unique real one in both, then I know it's real. And so these are the kinds of tricks you can do, observing that Newton's method is a real operator. It takes real input and sends it to real output. Okay, so I think that's the big picture for certification. Let me just check my notes. Yeah, any questions? What are the common pitfalls? One common pitfall is you accidentally computed a soft certificate instead of a hard certificate. you gave out the certified floating point numbers instead of giving it exact numbers, and so you're still probably right, but hopefully your round off didn't make you wrong. So that's one common pitfall. Another common pitfall is you have a system and it's not square, and you try to do this. Now, of course, you can't because there's all these Jacobian inverses flying around for Newton's method. So you can't do it with a non-square system. So you might naively think, okay, well, I'll square it up. And then I'll certify what's going on with the squared up system. And that's an issue because when you square things up, we learned that you introduce new components to the solution variety. Okay, you're really changing things when you square up a polynomial system. All right, what else? Maybe those are the biggest common pitfalls here. Yeah. Okay, so now are there ways to handle non-square systems? Yes, I'll link to it in the notes. These notes are essentially going to be a lot of links because I think just these papers explain it better than I really can. So I'll give you a brief overview, and if you want more details, check out the papers. So yeah, so Tim Duff, Nick Hine, and Frank Stive have done some work on certifying non-square systems. What else? Next class, we'll talk about more exotic certification questions. One there. So this is not the question we answered today. Today, we had approximate solutions to polynomial systems and nobody was told how we got them. Could have been by homotopy continuation. Could have been by God speaking to me in a dream. Okay. Either way, I have some solution I can certify. What would it mean to certify homotopy continuation? Certifying homotopy continuation means certifying the actual bijection you get from start solutions to target solutions. Okay. Much harder than certifying these like static, unmoving points. Okay. The answer is yes. And I think very recently we have effective methods, and in the past there have been like proof of concept methods that can honestly prove things. But now it seems like we have a general effective method, and I think everybody's just kind of waiting for it to get implemented in an easy to use place. What about monodromy? What about degrees without upper bounds? Okay. So the 27 lines on the cubic have a Bezier bound of 81 and a BKK bound of 45, even though there's only 27 solutions. So I can find the 27 solutions. I can certify that I found 27 regular solutions. And the parameter continuation theorem tells me that the generic number is at least that much then. Okay, so that's all great. But can I prove that it's 27 without relying on Haley and Salmon from late 1800s, or a Grosvenor basis or something like this? Can I actually prove it? Okay, so that would be proving degrees of polynomial systems. What about degrees of varieties? How do I know? Like, I can prove that I found a bunch of points in a witness set. How can I prove that I found all of them? We have a method for verifying that we have all of them. It's called the trace test. Can you certify the trace test? So certifying the trace test would be a huge breakthrough in numerical algebraic geometry. It would reduce the problem of computing degrees of all these specific varieties, really to just a large computation. Whereas right now we only get 1/2 of that with certification. Okay. And that's what's at the core of the theory exercise 2 this week, is even if you could do everything exactly, you don't have to worry about numerical approximation. Could your trace test still give you the wrong answer? Okay, and the answer is yes, it could. It heavily relies on you using a generic parallel slice. Okay. And yeah, so we'll just we'll talk about extending the certification methods we've talked about today to other instances, and what kind of theorems you can prove on a higher scope. Yeah. Okay. And then of course we'll do computations on our last day, and it will be lovely. Okay, see you all on Thursday. Thank you.